So here in section 5.2, we are going to get really into more of the nitty-gritty of an actual exponential function, now that we've got a little bit of the algebra of exponentials behind us to support us. And so here's our definition of this new function family, exponential functions. Okay. As previously mentioned, these are the first non-polynomials that we'll have looked at in this class. So here we go. Our exponential function has this form. There may be a constant multiplier, which is this a. You'll have some base b, and the variable this time is going to be in the exponent, so b to the x power. Notice this is the defining feature of an exponential function. The variable contains the exponent, right? Remember, that was not true for polynomials. Polynomials had exponents of like x squared for quadratics, or x cubed, or x to the fourth, and so on. But the variable was not in the exponent with polynomials. So this is my general form then for an exponential function, a times b to the x. Just to highlight that difference again, back in our power functions section, we had constants as the exponents, x to the sixth, x to the third. We now have variables for the exponents. Okay? These are power functions. These over here are exponential functions. All right, so we're ready to start investigating this new kind of function, this f of x equals ab to the x. And as is typical when we look at a new function, we usually want to see what the graph looks like. And we'll draw our first graph by hand to get a feel for it. And then after a while, we'll start talking about some shortcuts for graphing. So my function this time is 3 times 2 to the x. Notice 3 is the a, right? Remember, f of x equals a times b to the x. So 3 is the a here. The base is the b, 2. And then our exponential x is where our variable is. All right, so let's start plugging some stuff in here. If I would like to put an x value of -3 into that function, I would have 3 times 2 to the -3rd power. Remember that the negative exponent moves that to the denominator. So that's 3 over 2 cubed, or 3/8. Same idea here. I'd have 3 times 2 to the -2nd power, which is really 3 over 2 squared, 3/4. And when x is -1, 3 times 2 to the -1st is 3 over 2 to the 1st, 3/2. All right, we're going to plug 0 in for the x. So 3 times 2 to the 0. But of course, any number to the 0 power is 1. So that's really 3 times 1, which is 3. When x is 1, 3 times 2 to the 1st. 3 times 2 is 6. Plugging in x equals 2. 3 times 2 squared would be 3 times 4, so 12 here. And then finally, I want to plug in x equals 3. 3 times 2 to the 3rd. That's actually 3 times 8. So that one's 24. All right, take a minute and plot those points on your graph. You'll have to do a little estimating with the fractions, but that's okay. So -3, let's see, the vertical axis, by the way, looks like it's going up by 2s, so watch out for that. -3 3/8 is going to be way down here. -2 3/4 is just slightly higher, a little bit less than 1. -1 3/2. 3/2 is 1.5, so getting a little bit closer to the 2. 0 3. 1 6. 2, 4, 6, 212. Sorry about that. That last one, I didn't go far enough. Let me fix that. It was 1, 6. 1 is over here. So 1, 6. There we go. 212, 10, 12. And then 324. 3, 20, 22, 24. So there are the points that can be plotted for this function. And you'll notice that this does look different than anything we've seen so far. It starts out very small and it goes up kind of slowly at first, and then it goes up much more rapidly later on. If I were to sort of connect these with a fairly smooth curve, kind of look like that. And we can see pretty clearly that this end behavior is going to go up to the right. But I'd like to talk a little bit more about the left-hand side. We've seen these really small fractions over here on the left. Will this graph eventually go down far enough so it'll cross through the x-axis and give me negative answers? I would say no. Think about these values when x was negative, right? The negative x put a negative in the exponent, which resulted in that factor going down to the denominator. But notice it's not a negative number. It's just something in the denominator. So these values over here, although they'll be very small, because you'll have bigger and bigger numbers in your denominator all the time, will never actually become negative. So I'm going to show that by just sort of sketching this in and showing that I'm really, really close to 0, but I stay above the 0. We'll talk about that behavior a little bit more in just a minute. So as we look at this graph has no x-intercepts, right? Never crosses the x-axis. As far as the y-intercept, I can see it here when x is 0, y is 3, and I can see it plotted here as well when x is 0, y is 3. And as a matter of fact, I can really kind of tell where that 3 came from. Right? When you plug in 0 as your exponent, any base to the 0 power will be 1. So all you're ever going to get is that multiplier, that a value. And we'll see that again. I'll make a note of that. All right, as far as local maximums and local minimums, again, there are none, right? There's no top of a hill, no bottom of a valley here. So no local max or local min. And this function is increasing everywhere, right? Just starts small on the left-hand side and it keeps on going up. So as far as an interval of increase or decrease, it increases from negative infinity to infinity. Never decreases. All right, ready to talk a little bit more about this behavior. We said that this graph was going to get very, very close to the x-axis, but won't actually touch it, won't actually cross it. This kind of behavior where we get really close to a line but don't touch it is called an asymptote. And because the x-axis is a horizontal line, in this case we call it a horizontal asymptote. It's simply a horizontal line that the graph approaches but does not touch. So the horizontal asymptote for this graph is the x-axis, which has equation y equals 0. And usually when we draw a horizontal asymptote, we don't want to mistake it as an actual part of the graph. It's more of a guideline on the graph. So usually we draw it with a dotted line. And let's just do that right now. this x-axis, my horizontal asymptote. And draw that as a little dotted line. Graph gets close to it, but doesn't actually touch or cross it. That, by the way, leads us into a discussion of end behavior, which I want to do right down here. It's not on here, but I want to add it. If I wanted to discuss the end behavior of this graph, it's clearly going up to the right. That's familiar, and we can put that in right away. But the left side is the side with the horizontal asymptote. So this graph is approaching the line y equals 0 on the left. It's approaching that horizontal asymptote. So up until now, all of our end behavior has either been up or down. We now have something new to add. With these horizontal asymptotes, we may approach a particular y value. And again, that behavior is due to that horizontal asymptote. All right, so I've got one exponential function graphed, and we're going to go ahead and graph one more by hand, and then we can start talking about some conclusions. This time, my function is going to be, my a value is going to be 4 multiplied by the base 1/2 to the x power. So once again, I want to plug in a few different values of x and calculate the y. I'll plug in -3 for the x. Let's see. That would be 4 times 1 to the -3rd over 2 to the -3rd. I'm going to flip those to make the exponents positive. So that's really 4 times 8 divided by 1. And 4 times 8 is 32. All right, let's plug in the -2. 4 times 1/2 to the -2 is 4 times 1 to the -2 over 2 to the -2. Again, to make those exponents positive, I'd have to put the 2 squared on top and the 1 squared on the bottom. So that's really 4 times 4, or 16, divided by 1 is still 16. All right, our exponential skills at work here. X is -1. 4 times 1/2 to the -1st would be 4 times 1 to the -1st over 2 to the -1st. And again, I'm going to have to move those across the fraction bar. 4 times 2 to the 1st over 1 to the 1st is 4 times 2, or 8. All right, I'm kind of happy to see that 0 because I think that one's going to go a little easier. If I plug in x equals 0, 4 times 1/2 to the 0 power is just 4 times 1, so that's 4. When x is 1, 4 times 1/2 to the 1st, 4 times 1/2 is 2. Getting there. 4 times 1/2 squared is 4 times 1 squared over 2 squared. It would be 4 times 1 over 4. 4 times a fourth is 1. One more. When x is 3, 4 times 1/2 to the 3rd power 4 times 1 cubed over 2 cubed would be 4 times 1/8, 4/8, or 1/2. All right, a little bit more work there getting our y values, but good practice for us in using those negative exponents, honestly. Let's graph this. The negative 332, I can't even get that on my graph. I don't have enough space, so I'm going to start here at negative 216. 10, 12, 14, 16. Negative 1, 8, 2, 4, 6, 8. 0, 4. 1, 2. 2, 1. And 3, 1/2. Hopefully what you're seeing here is almost like the previous graph we did, except flipped backwards, right? This time, it's the right side that's coming in and getting really close to the x-axis, and it's the left side that's getting really large. I kind of skipped over this a little bit before, but I'm ready to talk about it now. This is called an exponential decay curve because it decreases or decays away. This one was called an exponential growth curve, right? Or it's growing. And we'll come back and talk about that a little bit more later. But let's finish filling in our information here. The x-intercepts, once again, there are none. This graph does not cross the x-axis. And the y-intercept is here at 4. I can see it over here as well. When x is 0, y is 4. And once again, that's not a coincidence. That's the a value. Because when I plugged in x equals 0, whatever my base is to the 0 power will always be 1, meaning I'm always going to get the a value there for my y-intercept. Just like last time, there are no local maximums or no local minimums. In this graph, as far as increase and decrease, and we always read left to right, notice this one's going down all the time. It's always decreasing. So it decreases from negative infinity to infinity, but never increases. Before I talk about end behavior and the horizontal asymptote, now that I've kind of gotten that far, I want to go back again to the vocabulary. This we said was an exponential growth curve. And again, that idea of growth is really tied to the fact that it's always increasing. It's always growing. This one that we said was an exponential decay curve is tied to the fact that it's always decreasing. We're going to talk about this a little bit more on the next page, but we've already seen that the a value here is what gives us the y-intercept. The b value, the base of these exponential functions, is what determines whether it's a growth curve or a decay curve. So here, the b value is 2, and we got exponential growth. On this one, the base is 1/2. And we got exponential decay. Although I know it's just 2 examples, I'm going to tell you that in general, it will always be true that when we have a base larger than 1, we get the growth. And when we get a base smaller than 1, we get decay. Hopefully, again, that makes sense. When you're multiplying by something smaller than 1, your graph keeps getting smaller. When you're multiplying by something bigger than 1, your graph keeps getting bigger. All right. We again have a horizontal asymptote. Let me go ahead and add that. I'm going to draw that on the graph. We do like to use a dotted line for our horizontal asymptote. We can see the graph is getting really close to the the x-axis rather, over here on the right-hand side. So again, the horizontal asymptote for this graph is the x-axis, also known as y equals 0. And I can use that idea to write down what my end behavior looks like. This graph goes up to the left. And on the right side, it approaches the horizontal asymptote. So it approaches y equals 0 on the right. All right. Next page is mostly going to be a summary page. But there's one more thing I want to talk about before I'm quite ready to do that summary. I want to look for patterns. You may remember way back in one of the early chapters, chapter 2, I think, when we first looked at the tables of values for linear functions, we were able to see a pattern, right? When x went up by 1, y went up or down by a constant amount. And that turned out to be our slope. We didn't see those same kinds of patterns in the quadratic or the cubic or the quartic functions. But I'd like to know, do we see any pattern in these exponential functions? So these are just the same two tables that we just finished making. Just put them here for your convenience. And I want you to notice in both tables, my x values are going up by 1. And my question is, what's going on with the y values? Now, it may be easiest to see if you look at the whole numbered y values. Do you see here that they're not exactly going up by the same amount, but rather they're being multiplied by the same value each time, right? We're multiplying by 2, multiplying by 2, multiplying by 2. That same pattern occurs with the fractions as well. It's just a little harder to see for most of us. So my base, 2, is really just the constant multiplier of those y values. So there is a pattern. It's different than a linear pattern. It's a multiplication pattern rather than addition or subtraction, but it's still a pattern. Does it follow over here? Again, I'm going to look at the whole numbers because they're a little bit easier. As x goes up by 1, what's the pattern in the y's? Most people say, hey, it's half, right? It's being multiplied by a half. Sometimes people see it as divided by 2, but I want to encourage you to think of it as multiplication. This is 32 times a half would be 16. And 16 times a half would be 8. Half of 8 is 4, and so on, right? So once again, we have a constant multiplier. The constant multiplier just happens to be a fraction here. And it's exactly the fraction that formed the base of the exponential function. So we now kind of know what both the base and the multiplier do, right? The multiplier was our y-intercept. The base is the constant multiplier here. So I should probably start calling this the coefficient. The coefficient is our y-intercept. Coefficient is our y-intercept. The base is the constant multiplier. All right, we're ready to make this formal now. What we're noticing here is actually one of the very most important features of an exponential function. We say that an exponential function has a constant relative rate of change. Back when we were talking about linear functions, I mentioned that we called that the absolute rate of change. When something is changing by an addend or a subtraction, we say that's the absolute rate of change. That's the amount that it's going up or down each time. When something changes by a multiplier, we call it the relative rate of change. So just a quick comment there. In linear functions, we had a constant absolute rate of change. The y's went up or down by the same amount. But here, we have a constant relative rate of change because every time my exponential function, my x increases by 1, y doesn't get added or subtracted. This time, y is multiplied by the same amount. And that's a distinction we're going to come back to a number of times. Let me highlight that one more time. With the relative rate of change, the exponential function, y gets multiplied by the same amount. In a linear function, the absolute rate of change, y is added or subtracted by the same amount. Okay. Multipliers are exponential functions. Constant adding or subtracting is a linear function. All right, let's do a little bit more. Let's see. Oh, you know what? I can be more specific. Not only is y multiplied by the same amount, but I could even say I know what the multiplier is, right? The multiplier was whatever the base was. Multiplier is what the base was. So I can see it's multiplied by the same amount, b. All right, so now that we know what that base b does, we also know what a did, right? We said that a, the coefficient, gives us the y-intercept of the graph. Okay. And again, it makes sense since when x equals 0, your function would look like y equals ab to the 0 power, and anything to the 0 power is 1. So we just end up with a. When x is 0, y is a. That means a is our y-intercept. All right, well, that gives us a lot of information about the relationship between the a and the b values and what we're seeing on the graph. Now that we have a basic idea of what the graphs of exponential growth and decay functions look like, we can also graph other exponential functions by using transformations of graphs, which are going to be the same types of things that we've seen already a couple of times. Okay. In the case of exponential functions, the first thing we're going to do is to identify the parent function. And of course, that means deciding whether we have exponential growth or exponential decay. So if our base is larger than 1, we have our exponential growth. Which looks like that. A is the y-intercept. And if our base is smaller than 1, we have the exponential decay. That's the one that's decreasing, looks like that. Again, where the a value is the y-intercept. So one of those is going to be the parent function each time. And I can tell which one just by looking at the b value and whether it's bigger than 1 or smaller than 1. After that, all of my same transformations that we've seen before are going to work. So if I have a multiplier in front of it, that's really just a vertical stretch. This happens all the time. We've already really talked about that a value. It's that vertical stretch or shrink. But we see it as the y-intercept. So we already have a lot of information about what that multiplier does. If I have a negative in front of my function, in this case it would be negative ab to the x, that negative multiplier does what it's always done in the past. It's simply going to reflect my graph across the x-axis. Flips it upside down, right? If I add or subtract something to the x inside the parentheses, these are my horizontal shifts. So let's see, this would be a times b to the x plus h, which is going to shift us to the left by h units. And if I have ab to the x minus h, that's going to shift me to the right by h units. Again, the same exact thing as it was doing with our polynomial functions. Those transformations of graphs have not changed. The last two, where we're adding or subtracting something outside of the parentheses, these are our vertical shifts. So if I've got my function ab to the x, and I add k units to that, that's going to shift up k units. And if I have my exponential function ab to the x, and I subtract k, that's going to make it shift down k units. So again, these are the generic forms. This is what it looks like specifically for our exponential functions. All right, so if I think about my exponential growth and decay functions, graphs both, let's think about what I'd want to concentrate on when I was doing these shifts. Probably one of the most prominent features of these exponential graphs is the horizontal asymptote. So I always try to make sure I've shifted the horizontal asymptote and I have that in the right place. The second thing I'll usually shift is the y-intercept because it's a point that I can locate easily. So when I go to graph these things by our transformations of graphs, I'm going to shift the horizontal asymptote, I'm going to shift the y-intercept, and then I'm just going to sketch the rest of the graph around those two things. So let's try a couple. I'd like to sketch the graph f of x equals 2 to the x minus 3. Now, I probably should have had one more thing up here, and I'm going to add it. Let's talk first about the parent function. My base here is 2. And since that base is greater than 1, I know this is going to be exponential growth. I don't have a multiplier in front of the 2, so I can assume that my coefficient here is 1, multiplier of 1. So a is 1, and that defines my y-intercept. So I'm thinking kind of in my head, y-intercept is 1, exponential growth would look like that. All right, now let's start talking about transformations. The only thing that's been done to this is the -3, and that is not inside the function. It was done outside, so it's a vertical shift, down 3. So I'm going to do my shifting right now. I'm going to say, to shift the horizontal asymptote, which was on the x-axis, down 3, I'm just going to draw my little dotted line here down at -3 this time. So there's my new horizontal asymptote shifted down 3. The equation of that line would be y equal -3. And so if I'm asked what is the horizontal asymptote, that's it, y equal -3. All right, the other thing I want to shift is my y-intercept, which was at 1. I'm going to shift it down 1, 2, 3. It's here now. And then I'm just going to sketch in the exponential growth function. It gets small and approaches the horizontal asymptote on the left side, and then it gets large on the right side. Right. Domain and range. We haven't talked about those for exponential functions, so this is a good time to start. The domain here, this goes to the left forever, and although it's going up, it's also going to the right forever. So yet again, we have a domain that goes from -infinity to infinity. That is still not going to change. All exponential functions have -infinity to infinity as their domain. The range, however, is a little bit interesting. This function is always above y equals -3, and actually it never quite touches the -3. So I'm going to say my range goes from -3 to infinity, but I have to use a parenthesis on the -3 to show that it doesn't actually touch that. Okay. And let's just add end behavior to this as well. This graph goes up to the right, but on the left side, it approaches y equals -3. All right, so decent analysis of that graph. Let's try another one. All right, and again, I'm going to go ahead and I'm going to add a little information about a parent function up here. I think I need to rework this page. Let's see. My parent function this time, since the base is 3/4, which is smaller than 1, it's going to be exponential decay. So this is the one that decreases or falls from left to right. A value here is 3. So just kind of visualizing that. My y-intercept would be at 3. And this one's large on the left side, and then it falls and gets small on the right side, exponential decay. All right, in terms of transformations, this has been moved to the right 1. Notice that -1 is up in the exponent. It's not being done to the whole function, so it's a horizontal shift. Right 1. Think about your horizontal asymptote. Does shifting that to the right 1 actually change it? It doesn't, does it? Moving it to the right 1, it's just going to stay at the same y value, the same level here. And since it goes all the way from -infinity to infinity, a move right 1 doesn't really change anything. So I'm going to say my horizontal asymptote this time is going to stay on the y-axis. Stay on the x-axis, which would have equation y equals 0. All right. My A value was 3, so the y-intercept was 3. That I can move to the right one. So I'll move that over to here. And other than that, I'm just going to sketch in an exponential decay curve. Falls and gets close to 0 on this side, and gets large on the left-hand side this time. All right, our still boring domain still goes from negative infinity to infinity. And the range this time, the smallest y value is just above 0. So I'll put a parenthesis at the 0, and then the y values go up to infinity from there. If I wanted to write down my end behavior, this graph goes up to the left, and it approaches y equals 0 on the right. All right, we have one more graph. I think we'll do one more graph in this video, and then we'll talk about the equations in the next one. So here, we are supposed to sketch the graph of f of x is negative 1/2 x, or negative 1/2 times 3 to the x plus 5. So notice the base here is 3. So if I add some information about my parent function up here, base is 3. Since that's greater than 1, we're back to exponential growth. The a value is 1/2. The negative I'll deal with as a transformation, but for right now I'm going to say a is 1/2. So that would be my y-intercept. And exponential growth is small and then grows bigger. And again, that was 1/2 there at the y-intercept. So that's my parent function. As far as transformations, there are two things that are happening here. First, that negative sign reflects it over the x-axis. So it turns it upside down. Secondly, the plus 5, not in the exponent, but outside of it, that's a vertical shift. So we're going to go up 5. All right, let's see what we can do with this. Let's start with my horizontal asymptote. Was the x-axis, but it's gone up 5. So from the x-axis going up 5, it's going to put my new horizontal asymptote up here at y equal 5. Now, if it weren't for the reflection, I could just go ahead and kind of sketch this in. But because of the reflection, I have to think about what's going to happen when I flip that graph upside down. So instead of my y-intercept being 1/2 unit above the horizontal asymptote, it's actually going to be 1/2 unit below. Imagine this graph flipped upside down. So it's going to come up and get really close to the horizontal asymptote on that side. And then the growth is actually going to turn upside down. It's going to grow in the negative direction this time on that side. All right, domain still negative infinity to infinity. The range, this graph is going all the way down to negative infinity. And then it comes up almost to y equals 5, but doesn't quite touch it. So we'll go with 5 with a parenthesis. And as far as my end behavior, let's see, goes down to the right. And on the left side, it approaches y equals 5. So approaches y equals 5 on the left. All right, so that's our graphs. We haven't started with the equations yet, and this is probably long enough for one video, so I'm going to go ahead and pause here, and then we'll pick it up from this point and finish the section in a second video.